we at Delta Research often get questions about online DGA monitoring and what type of monitor should they get, or more specifically, how many gases should we be monitoring? And it really depends. And how does that fit into your transformer maintenance strategy? So we're going to talk a bit about that and try and quantify it a little bit in terms of how you can guide your thinking. And and in that context, let me just get my pointer ready. Pointer, and I can move. So we'll just touch on what is a maintenance strategy. Can DGA contribute to reliability-centered maintenance, which is sort of the ultimate method of or maintenance strategy that's out there that people talk about. We'll just touch on what are the breadth of online DGA monitors, cover some basic transformer failure data, so to set up the value calculation of DGA monitors, both on an individual basis and how you might apply particularly a constrained budget, not that any of us have any budget constraints, across a transformer fleet. And then we'll just wrap it up with some conclusions. But just a little disclaimer before we jump into this, I want to be really clear. Insulating liquid tests don't generally determine the condition of a transformer. They give you clues, they raise a flag, say, hey, the condition's changing, but you typically have to do other tests to find out what's actually going on or to confirm what's going on with the transformer. The DGA tests are good at pointing you in the right direction. And they do, the insulating liquid tests can give you good information with respect to oil quality, the condition of the insulating liquid, of course, but the transformer itself requires other offline tests typically. Okay. What is a maintenance strategy? Well, you heard from my bio, I gained my education through the Navy. I was an engineer in the Navy, and our job was to keep the ship in fighting condition while we were in the middle of the ocean. And we learned all sorts of approaches to maintenance. And I figured, okay, this should be straightforward. I should be able to go grab some information, borrow it, so that we can present it and just sort of discuss it in the general context. And I was actually surprised how many different terms out there and how many versions of PM there might be. And then there's so many P words my kids thought I was being rude. But I found one that sort of simplified it to what I think is is appropriate. Borrowed this from Reliable Plant magazine. This was for an article that was talking about reactive maintenance. It can be an effective strategy, which is basically a run to failure type approach. Now, the one thing I'll say here is, in the research I was doing and preparing for this talk, the articles I'm reading all refer to each one of these lines as a separate maintenance strategy. And I don't really agree with that. The maintenance strategy really is, you have a broad set of assets and various criticality, various costs, and your strategy is, how do you apply all these approaches or philosophies across your fleet? Okay, and that's really what you need to think about. Is it's not one size fits all for your fleet. Why I like this is it's fairly simple. The reactive is a run to failure type. Preventative maintenance is just doing stuff on a predetermined schedule. And we're talking about maintenance, not inspection. Inspection is typically, you're doing that on a predetermined schedule too, but that's to help tell you when things need further investigation. So DGA actually contributes to a condition-based, or what they relabel here as predictive based maintenance, because you need to constantly be aware of what's going on, understand what the condition is and when it changes, so that you can go and actually do some maintenance. And then RCM is reliability-centered maintenance, which you're actually on an ongoing basis, rolling up your sleeves in those failures, understanding the failure mode, understanding what led up to it, and trying to apply those learnings to the rest of your fleet. And you can see that the cost to implement, goes from low up to high. typically because it requires more work, more time, more effort, might require more equipment, sensors. And the one revision I'll make to this slide is we're not fans of the term predictive at Delta X Research because nobody has that crystal ball which will tell you exactly when an asset will fail. So you're really saying, hey, the condition is such that it should be taken care of. We prefer to call it condition-based maintenance, or CBM. Okay, can DGA fit into a reliability-centered maintenance strategy? And the answer is yes, it can contribute to it. We have found that if you take your DGA data and you can convert it to a fault energy index, which is basically saying, hey, how much energy went into that failure or into that incipient failure, that problem that's going on, how much energy has gone into that that's been expended to create the heat that creates the gases. And what's really nice about that is if you think about DGA, the gases are actually a symptom of the actual problem. The problem is a loose connection. Oh, it might be your windings are twisted and causing a short, whatever it might be, that's the problem. And the first symptom that's coming out of that is that some energy is being expended and is generating heat. There's the first symptom, and that heat is then cooking your insulation, whether it be paper or oil, which is creating the gases. That's your second layer of symptoms. And you really want to get closer to the root problem. And the fault energy index helps you do that. You now understand how much energy is going into the fault. And what we learned is that the likelihood of failure changes as the fault energy index increases. Okay, so if a transformer has never gassed before, doesn't matter if it's a brand new transformer or a 30-year-old transformer, if it starts gassing, the likelihood of failure will rise very quickly, come to a peak, show a certain level of robustness, and then gradually start coming down as demonstrating a very robust transformer. You don't want to ignore it, but the sense of urgency might diminish somewhat. So what this is a model based on a statistical analysis of a large population of transformers. So this curve does not represent any single individual transformer. It represents a large population that has created this model for us. So what do we do with this model? Well, now that we have it, you can take any particular transformer of interest and compare it with the model. So you calculate the current fault energy index for a particular transformer. That's what this dotted line represents, and place it on top of the model. And when you look at that, you can look at the area under the curve to the left of that dotted line. That's referred to as the cumulative severity. And it's basically saying how lucky you've been that you survived this long. Okay, it indicates the percentage of transformers that if they had been gassing, that would have failed before reaching that particular level of fault energy. If the transformer is still gassing, then you figure out what its rate of gassing is. At that rate of gassing, we can figure out how far up to the right the transformer will move over the course of the year. And you look at the area of that basically indicates what the likelihood of failure is over the next 12 months. We refer to that as the hazard factor. So that gives you a sense of how at risk you are going forward of continued operation. Now we've been asked, we've done a lot of work on this in the context of looking at all the key gases, the hydrocarbon gases, all of them, and all the carbon dioxide gases as well. And we've also, a number of customers have been asking us, what about hydrogen only? Can we do this for just hydrogen or composite gas monitors? And today I'm going to, single gas or composite gas or hydrogen. I'm just going to use hydrogen, but just know that it applies fairly generally. And yes, a similar curve does exist for hydrogen. And so let's now talk about the online DGA monitors. You're mostly familiar with this, but we've come to realize that really the breakdown is you look at, when it comes to DGA, single gas or hydrogen at the bottom there's 4 to 5 gas monitors, and and which cover the essential gases and allow you to apply the Duval triangles. And you have the full 7 to 9 gas DGA monitors, which if you look at the top, you can measure all the key gases. Some of them also measure oxygen and nitrogen, which will give you an indication of whether the transformer might be leaking. I think you can do it with all the 7 to 9 DGA gas, 9 gas monitors have some form of leak detection, and they all provide a ability to do a comprehensive interpretation of the gases, including your fault type diagnosis with Duval triangles or 4-simplex. You can do an advanced carbon oxide interpretation looking at CO-CO2 ratios. And, as I showed in the previous curve, you can do a reliability analysis. There's a range of prices. I'm just picked a number at the $45,000 number as a nominal range, somewhere mid-range. And our work has shown that for all the failures that we've seen that are related to DGA, applying these methods and the reliability analysis can generally will detect about 80% of all the failures before they fail, okay? Or can detect them before they fail. So you have an opportunity to avoid 80% of potential failures that are related to DGA. And then you get down to a 4 or 5 gas DGA monitor, it gets all the essential key gases. Typically, it's only one of the carbon oxide gases, so you can't do a full carbon oxide interpretation, but it is pretty effective. It can identify events occurring in the liquid and the vapor. It's got all the information you need for the Duval triangles or the 4-simplex, and you can do a reliability analysis. Hydrogen, it measures a single gas. So it'll tell you when the events are occurring, and you can do a reliability analysis, as I mentioned earlier. And I should mention, of course, the prices are coming down. And hydrogen, we found, our studies are showing that it will detect about 40 to 50% of the problems out there. Not nearly as good as a full multi-gas monitor, but still pretty good. We haven't done a thorough study on 4 to 5 gas DGA monitors, but we think it'll be closer to the 7 to 9 gas. So hence we just put an estimate of about 70% detection rate there. Okay. So understanding the cost, you have to look at the cost over the course of the life of the monitor, and we're just assuming a 10-year life for the purposes of this discussion. And you just allow for the fact that you've got your initial capital costs, you have communications you have to add on, there's installation costs, and there may be some data processing costs to do your reliability analysis. And you look at the cost in year 1, and then you have the costs of years 2 to 10, add them all up, and there you have your 10-year cost of ownership. These are very simple numbers. We're not doing net present value or anything too sophisticated here. The whole point of this is to sort of get you thinking about, where do you get the most bang for the buck? And you're going to have to do your own calculations, but you basically follow this approach, and then you can add some layers of sophistication if you wish in terms of layering in net present value and stuff like that. But most of the cost is at the front end, so net present value probably won't have a big impact here. Okay, that's the cost of ownership. What's the failure rates? Well, I referred to the same reliability study that Brian just referred to from Seagray. And what's the failure rates? Well, there was a wide range of failure rates. Throughout all these studies, you can see here in this column, I said 2%, less than 2, 1 to 2, some low numbers. So for the purposes of this discussion, again, and you're going to have to decide for yourself what the right answer is based on your own experience. But I was assuming that the low typically is around 0.5%, the high tends to be about 1.25%. So I just took a mean or an average of 0.88% for the purposes of this discussion. Okay. Also referring to that survey, you look at all the failure modes or the components that were involved, and we have to pick out those components that actually might be detectable by DGA, because DGA won't detect typically a bushing failure. And so when you add them all up, about 43% of all the different failure modes can be detectable by DGA. Why are all these numbers important? Because you really want to figure out, well, what is the actual opportunity for you? You know, what's the benefit you might get when you deploy a online monitor? And this is how you go through the calculation. What is your annual transformer rate? Well, there's the 0.88%. How many failures are detectable by DGA? There's the 43% number. And then looking at the different types of online monitors, what's the detection rate? Okay, well, in the case of a multi-gas monitor, 80%, hydrogen picked 45%. And so what's your potential annual failure avoidance? And it comes down to 0.30%. Well, that seems like a really, really low number. Who cares? But when you're talking about assets that are worth millions of dollars, that can really add up materially. And put it in a different context, you may be able to avoid up to 34% of potential failures that are related to DGA. So that when you have a large fleet, that's very worthwhile for your organization. And you notice that hydrogen, is not quite as effective, but it's nothing to sneeze at. You still, if you can avoid 19 or 20% of all failures, that's worth consideration. Well, how do we apply this in terms that your CFO will appreciate? Clearly, it's all about the dollars. So what's the value? Now we're going to look at this for an individual transformer. And here I picked what's the consequence of failure in financial terms? In this case, I picked 1.25 million. Getting into how you calculate the consequence of failure, that's a whole nother discussion, a whole nother paper, so I'm not going to delve into that. But you take your potential annual failure avoidance number and say, okay, the annual benefit of deploying any one of these monitors is this line here, ranging from $3,700 for a multi-gas monitor down to a little over $2,000 for a hydrogen monitor. The planned life is 10 years. A simple multiplication, the benefit you might get from a multi-gas monitor is in the order of $37,000 or $38,000. And a hydrogen monitor, $21,000. Subtract the 10-year cost of ownership, and your benefit is negative on a multi-gas monitor, and this is where you're basically at the break-even point for a hydrogen monitor. So, in this particular example, you should not deploy probably any monitor at all. If you really, if your organization has a policy of monitoring as much as possible, you shouldn't deploy a monitor anything that's less valuable than $1.25 million. And you should just stick to manual DGA or pick a simple planned maintenance, preventative maintenance type approach to this, or even run to failure, which many do for very, very small assets. Example 2 is I'm here purposely picking the break-even points. So this is a consequence of failure of $2 million. Did all the same calculations running down. You can follow the numbers, and here we're just approaching the break-even point for the 4 to 5 gas monitor. And you can see, okay, now we're getting some material value of a hydrogen monitor. So here you might still, in fact, I would very much still just deploy a hydrogen monitor in this case. And you're still out of the money in 7 to 9 gas monitors. Example 3, where do we finally break even for a 7 to 9 gas monitor? Is that $2.5 million mark. And I don't think I need to run you through the numbers in detail again. But what if you stretch this really out? So let's look at the graph. What I have been identifying in those cases is the break-even point here along the x-axis. Now, this is the consequence of failure rising over time, or just rising. So in millions. So here's 2.5 million. This is where you break even on a 7 to 9 gas mother. 2 million for a 4 to 5 gas mother, and 1.25 million on the hydrogen mother. But what you want to do is see, where does it make more sense now? The hydrogen mother provides a lot of value here, right up until you get to about $3.5 million, and then it might start to make sense to deploy a 4 to 5 gas mother. Okay, and that's what you want to track to is, okay, up here, this is where when you're around $5 or $6 million in consequence of failure, that's where a 7 to 9 gas multi-gas mother makes a lot more sense. The multi-gas mothers, the 4 to 5 gas and 7 gas track fairly closely and rise together, but clearly it's the multi-gas 7 to 9 gas makes a lot more sense. And the hydrogen gas, what this does is open up a whole smaller class of transformers that it might make sense to deploy a hydrogen monitor on. And that's what you want to look at when you're looking at each individual transformer. And so if money was no object, don't know who has that luxury, but if money is no object, and you want to take an approach to deploy monitors on potentially all of your transformers, well, then you would simply look at this graph, calculate it for yourself, come up with your own numbers, but you want your own version of this graph, and then figure out where each individual transformer falls on this graph in terms of consequence of failure. And that would give you guidance in terms of what class of monitor to apply. But I don't have the luxury of a unlimited budget. I have a fixed monitoring budget. And in this case, I'm assuming I only have $1 million. And let's say I have a fleet of well, in this case, I'll say more than 48 monitors. Okay. And let's say, or 48 transformers, and let's say the consequence of failure is high, $2.5 million, and can be higher. It might be lower, depends how you deploy it. And again, I'm taking a very simplistic approach here to really exaggerate the point. In this case, with a limited budget, even though you're breaking even with a 7 to 9 gas monitor here, your hydrogen monitors are providing a lot more value, because even though the likelihood of finding a problem on an individual transformer might be less, you're able to look at a lot more transformers on an ongoing basis, because you can afford 48 monitors with your $1 million budget versus just 13 multi-gas monitors, 13 7 to 9 gas monitors. And that makes a big difference when you're playing the odds. Okay. And so what you really want to do then is, okay, what does that calculation look like as the consequence of failure rises? And you'll find in fixed budgets, depending on the mix of your fleet, it just may make sense to deploy hydrogen monitors across your whole fleet, because this is how the curves or how the lines diverge. And this is the type of thinking that we encourage our customers to do as they go through this thought process. I think I went through that fairly quickly. So really the message I'd like to get across here is the maintenance strategy consists of a mixed maintenance philosophies that apply to across your fleet, and you apply different approaches to different classes of transformers which is and there's a function of, you know, how expensive are those transformers and what's the consequence of failure. And if you consider the approach carefully, you can really enhance the value of those monitors and the data, including hydrogen only. I want to be important here. You can get good value from hydrogen data. And for individual transformers, you know, it's fairly straightforward. The greater the consequence of failure, 7 to 9 gas DGA monitors provide great value, but you get really good value for transformers with lower consequences of failure, which means that there might be a whole class of smaller transformers that you hadn't considered monitoring with that hydrogen monitors actually give good value on. And if you have a constrained budget, do the math. When you look at the odds, a fleet-wide deployment of hydrogen monitors may provide the best value depending on the size and mix of your transformer fleet.
Okay, first question. How is the fault energy index calculated? Is there any research paper available by Delta X to calculate it using dissolved gas analysis reports?
Yes, we point to them on our website. The initial work was done by Freddie Jacob, who many of you might know. He's one of our pioneers in this field. He's a chemist. And Jim Dukarm, our founder, mathematician, contributed to verify the math. And it's basically what you're doing is looking at the enthalpies of formation. How much energy does it take to convert a molecule of mineral oil to a molecule of each of the key gases? And you do the same for paper, and then you can use those as basically weights to come up with a fault energy index. So, you know, it's not perfect. You don't know exactly how much energy goes into the fault, but we've found that it has been very effective of doing a better sense of assessing the severity of faults than just simply looking at the gases on their own.
Next question. On slide 8, does this include LTC, regulators, and transformers greater than X megawatts?
So does the model include regulators, LTCs, and transformers greater than X megawatts?
Yes.
Right. So this is for transformers main tank only. Okay, so it only applies to that, doesn't apply to LTCs. LTCs, as we know, depending on the type of LTC, you know, you're going to get gas production regardless, and that's normal. So right now, this is only for transformers. It does not break it down by transformer class at the moment. There has not been enough failure data available to be able to go down and do sub-classifications of this. Certainly, we're working hard to collect more of that data. Our customers are being very gracious and sharing more and more data with us, and hence we're getting more refined in our analysis, and we hope to be able to classify the transformer fleets and have separate curves for different classes of transformers in the near future.
Okay. Next question. Do you have an example of a hydrogen monitor mounted on an XFMR? If you showed it, I missed it.
I did not show any pictures, so we don't provide hardware. You know, we would refer you to other vendors or who have hydrogen sensors out there or composite sensors out there. We've been collecting data though, and many even of the multi-gas monitors have hydrogen or deliver hydrogen, so we're able to just look at that data on its own.
What is is there a difference between the accuracy of online testing and offline testing?
Oh, am I allowed to say no comment?
Sure, if that's your answer, sure.
I you know, it really does depend. There's a wide variety there. It depends how careful people are taking care of their monitors, how careful, you know, and whether they're being calibrated on a regular basis. There's a lot of variables there. The labs too, you know, how diligent they are at taking care of their gas chromatographs and so on. They're all pretty good, but you know, we have seen variances over time.
I was taught many years ago that a transformer should stay with one particular lab over a period of time because different labs have different testing protocols. Is that true?
Yes, we have seen that.
Right. Okay.